Derivatives are all to do with tangent lines, which you guys have been working with. We've done lots of limits up till now. We have estimated slopes of tangent lines. Remember, we would do like all the secant lines and make all those tables and then see what value it's getting close to estimate our slope of the tangent line. That slope of the tangent line is what's called a derivative. Now, we could have actually been doing that with limits the whole time. When you think about what we were doing before, when I had some curve and I wanted the slope at point some a value here, then we were taking points, getting closer to it, and calculating all the slopes between those, right? We kept getting closer and closer. Like if it was 2, we do 2.1, 2.01, 2.001. So we were making the distance between the x and the number we were approaching get smaller and smaller. So we're really doing a limit as your x approaches that given a value. Because my a were 2. We were doing the limit as x got closer to 2. So now that we know how to do limits, and we have all these algebra techniques for doing limits, we could skip all those tables and just treat it like a limit. So let's look at this. I want to find the equation of the tangent line to this parabola at point 1, 1. So before, you would have made two tables. One with values bigger than 1 and one with values smaller than 1, and calculated slope at least 6 times and then estimated what your value was approaching. But now we can do it as a limit. So to find the slope, we are really just going to do the limit as my x approaches what value? 1. Of f of x minus f of a over x minus a. This is just your slope calculation. y2 minus y1 over x2 minus x1. So we're going to calculate the slope between these two things. So my f of x is my x squared minus 1 over x minus 1. If you need to, you can think about these as 2 points. 1, 1 is one of the points. The other one, if you put in x to find your y, you do x squared. And then I just did the slope between those. y2 minus y1 over x2 minus x1. You guys see where I got that? Alright, can I just plug 1 in here? But what could I do? Factor the top. So that would factor into x plus 1, x minus 1. So the x minus 1's cancel, so I've got the limit as x approaches 1 of x plus 1. So plug in, and we get 2. So our slope is 2. A little bit faster than making those tables. Now I asked you for the actual equation of the line. So you have a point, you have a slope, we can write our equation, right? Y equals mx plus b. So my y is 1, m is 2, x is 1. So we get y equals 2x minus 1. So much easier. Yes.
So the second order pair, I know you got x squared, but how'd you get the first x?
Just think about any ordered pair as x, y. So I just did that, and then I replaced my x with what y was equal to, or my y with what it was equal to. Other questions? Oh, just wait. Eventually it even gets easier than that.
What's the line representing?
That's the slope of the or the equation of the tangent line.
Okay.
So like, if you had this curve, you just wrote the equation for this line touching it. Other equations. There is a second notation that's sometimes used that really says the same thing, but it's written a little bit differently. It's the limit as h approaches 0 of f of a plus h minus f of a over h. In this, the previous one we did the limit as x approaches is a of f of x minus f of a over x minus a. The difference is here, a is just representing the distance between x and the value it's approaching. So if the distance between them is getting closer to 0, that's when x is approaching a. So it's another notation, really means the same thing. This is the one that we will probably use more frequently, just because sometimes it's easier to cancel an h off the bottom than trying to get rid of an x minus something on the bottom. But really they're interchangeable, you could use either one. So we're going to try using this notation, or using both notations to do a problem. So I want the equation of the tangent line to this hyperbola y equals 3 over x at the point 3, 1 using the second method. So the second method is the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, f of a plus h. What is my a value here? What x are you trying to get close to?
Oh, sorry.
3. My a is the number your x is getting close to, so my a is 3. So I'm going to do f of 3 plus h. So if you go to your equation, you replace your x with 3 plus h minus f of a, but my a is 3, so that's 3 over 3 all over h. Is everybody with me?
I don't see how those fractions came.
That's the equation, 3 over x. So I just plug those things in for x. Question? Other questions? So let's start simplifying here. 3 over 3 is 1. What are your ideas? What could we do here? Anything?
Could we split apart that first fraction and cancel out 3?
No. There's 2 terms on the bottom, you can't separate them. Common denominator is probably a pretty good option. So there are 2 approaches. We could just get the common denominator. It's not bad. So if we put this is just like 1 over 1. So what would you have to multiply by on the top and bottom? Okay, so we get the limit as h approaches 0, 3 over 3 plus h minus 3 plus h over 3 plus h. What are you going to have to do with this minus? Distribute it. So then 3 and negative 3 would drop, so we get negative h over 3 plus h. I'm going to go ahead right now. How do you divide fractions? Flip and multiply. This is like an h over 1. So I could take this times and then flip it, 1 over h. Then I can cancel an h out. So we get negative 1 over 3 plus h. And then you can plug in. Yes, Tim?
Okay, so you did, how do you get to cancel out on h out?
Got the same thing and then to plug into y equals mx plus b. So y was 1 equals m, which is negative 1/3, times x, which is 3, plus b. Add my 1 over, so b is 2. So my equation is y equals negative 1/3 x plus 2. Questions? Let's do it the same problem, but we're going to do the other method just so you can kind of see the difference between them. So the first method was doing the limit as x approached a of f of x minus f of a over x minus a. So we would have the limit as x approached 3 of f of x, so 3 over x, minus f of a, so 3 over 3, over x minus a, so x minus 3. So what do you want to do? Common denominator. One is the same as x over x. So you would get 3 minus x over x. This is x minus 3 like over 1, so if you wanted to multiply, flip and multiply, you could do that instead of writing a fraction within a fraction. Does anything cancel? I need that x minus 3 to cancel. Will it? Not quite. Is there a way to make it cancel?
To multiply by -1.
What if we just factored out a -1? If I pull out a -1, that would make this a -3 and a positive x. -3 plus x and x minus 3 are the same, so now they drop. We get -1 over x, which gives us -1/3. So same slope we got before. And then you would write your equation, y equals mx plus b. So two approaches, both are going to give you the answer. They just look a little bit different as you get there. What questions do you have? So this leads us right into velocities. We saw before there was a relationship between tangent and secant lines and velocity. Your average velocity was the slope of the secant line, instantaneous was the slope of the tangent line. Average velocity, like we've seen before, is just the slope between 2 points, distance traveled per unit of time. So that's nothing new. Instantaneous velocity is the same thing as the slope of the tangent line, so it's the same as that definition of derivative that we just got done seeing. Again, you could use either notation. I'm going to kind of start gravitating probably towards the second one, but you could really use either one. So that slope of the tangent line or the derivative, that is also an instantaneous velocity. Let's use that to look at a problem. Okay, so we are going to drop a ball. It is starting 450 meters above the ground. I think this was actually, did I do this exact problem when we did instantaneous velocities maybe? I think, when we made tables and used it to estimate then. Now we're going to do it this way. So I want the velocity of the ball after 5 seconds. And I'm giving you the equation I want you to use right here. We're going to use the motion equation, s equals 4.9 t squared. T is time in seconds and s is the meters traveled. So I've given you an equation to start with. So instantaneous velocity. The definition that I just gave you was the same as the derivative, so you could really use either one. I'll go with the second one. So it's the limit as as h approaches 0. Of the f of a plus h minus f of a all over h. Okay, so that's our definition. We have a couple options. I could go ahead, part A, I want the velocity after 5 seconds, so I could go ahead and plug in my 5 for my A. Part B, though, is going to ask me to find another velocity. If we leave A as the variable A for now, and go ahead and do all this, then we'll have a formula for velocity. And then we could just plug in as many values as we want and not have to recalculate this limit every time. So would you be okay with me leaving it in terms of A for now, so we can get a velocity formula, and then we don't have to keep recreating it? So, f of a plus h, this is the equation we're using. So we are going to plug that in. So 4.9 times a plus h squared minus f of a, so 4.9 a squared all over h. So I needed to FOIL all this out. Would it confuse you horribly if I factored out a 4.9 since everything has it? And then I could just FOIL this and not have to worry about the 4.9. So if you do a plus h times a plus h, you get a squared plus 2ah plus h squared. If I also pull the 4.9 out of that one, it would just be minus a squared.
Is it 2AH?
Yep. What happened now?
A squared is canceled. And you can factor, you can divide by 8.
Okay, so we could go ahead and pick an h out of everything. So I get 4.9 times 2a plus h. Okay. Is everybody with me there? Hmm?
Now you can plug in.
Now we can plug in if our h is 0. We get 4.9 times 2a plus 0. So that's 9.8a. So that's really our velocity formula. Then part A wants the velocity after 5 seconds, so all you would have to do is plug in a 5. And what do we get? Okay, part B wants the speed when it hits the ground. Do I know the time when this hits the ground? Can I find it?
Yes.
I have this formula for my height here. S is the meters that have been traveled. We started at a height of 450 meters. So when I hit the ground, how far have we traveled? 450. So if we divide by our 4.9, and then to find t, you would do a square root. Typically you do plus or minus, but can you have a negative time? No, so we just have to do the positive. And I get my t to equal 9.58. So to find the speed at that time, I can just plug it into the formula we found, so 9.8a, and my a is 9.58. And I get 93.884 meters per second. Questions?
I don't get why we had T, but then we put it in for A.
We wanted, A just represents the x value we're approaching, which in this case, t was the variable, the time that has passed. So we found how long it would take us to hit the ground. So that's our t, or the x that we're approaching, so that's the number we plugged in for A. So we had a lot of different variables floating around here. Normally we just have as x is approaching some A value, but in this case we had t. Okay, so all of these, I kind of already told you, these are just derivatives. So we've done the tangents, we've done the velocities. That is a derivative. A derivative is just a rate of change. And so these are things that come up a lot. That's why calculus is a major, or is a class that lots of science majors have to take, engineering majors, business majors, because it comes up in all of those different areas. So this is just one more time stating the two definitions in terms of derivatives. Before I called it tangents, then I called it velocities, derivatives. Those are all asking you for the same thing. So let's find a derivative. So same question, just phrased a different way. Find the derivative of this function at the number a. So you could use any of the notations that you wanted. We have the two definitions. A lot of times when we calculate derivatives, we call it f prime of x. So f of x is the original, f prime is the derivative. And then we're just using that formula. So the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so if I plug this in for my x, so we would have a plus h squared minus 8 times a plus h plus 9 minus f of a. So you go to this equation, you plug in an a, so you get a squared minus 8a plus 9. All over h. definition of derivative that we've done on the last two. So all I'm doing is plugging those variables into my function. So when I say f of a plus h, it means you go here, you replace your x's with a plus h.
How do you know like what the A and the H are?
We don't. I asked you to keep it in terms of the number a. So my final answer is going to have an a in it still. I didn't give you a number to plug in on this one. So the first few examples we knew a was 3 or a was 1. I didn't tell you on this one what a is. So our final answer will still have a in it. Other questions?
So it's just like saying f of 3 plus f of 2 or something.
Yes.
This is what we
It's
did
just
back
a-
in chapter 1.
Mhm.
Put A plus H into all the X's?
Yes.
It's like what we did back in chapter 1.
We did this part without a limit in college algebra when we did functions too. We called it the difference quotient. And you just had to evaluate those, and we usually just broke it into pieces. You would do f of a plus h, get an answer. Then you subtract off f of a, and then you divide at the end. I'm just trying to do it all together now. Right.
But on the other ones, we put in values to get
Right,
the
because I
equation that we've already gotten.
yes, because I gave you a number on those. This one I did not. I just said find it at a. So we're still going to have a in our answer. Other questions? Okay, how am I going to start simplifying all of this? Start multiplying it all out. A plus a squared will give me a squared plus 2ah plus h squared after you FOILed it. This one you have to distribute the negative 8. So negative 8a minus 8h plus 9. Still doing okay? What do I need to do at this point? Distribute that negative. So then when you add like terms, a squared and negative a squared drop. Negative 8a, positive 8a drop. 9 and negative 9 drop. Okay, so now what can happen? Divide everything by h. So now if you plug in 0 for your h, you get 2a minus e. So we found the derivative at a point A. That means you basically found a formula for the derivative. Now, if I told you to find it at 3, you could just plug a 3 in. Or if I said find it at 7, you could just plug a 7 in. Instead of having to make 2 tables for every single one of those values, you did the limit work one time, and now you have an equation. You could find the limit at any, or the tangent line slope at any of those points that you might want to plug in. Alright. Questions?
Is the A and X value?
Mm-hmm. So the next slide is really just stating what I just told you, that the tangent line has a slope equal to that derivative. So you could write an equation for a tangent line at any particular value. You would just plug in the x in for a, and you would get your slope. So using that then, find the equation of the tangent line to this parabola at the point 3, negative 6. So this was the problem that we just did. And we found out our equation for the slope was 2a minus 8, correct? So now you can plug in what's your a value?
3.
be. Add your 6 over. And you get your overall equation. This is the section we're going to be working on for the 3 days I have you this week. So we're going to work on this again Tuesday and Wednesday. The assignment is on the last slide. You can start that. That assignment will be due Monday. So you've got a week for that assignment.